Okay, thanks very much. Thanks very much for having me here. I'm really pleased to get a chance to travel here. So, yeah, so I was going to try to talk about the project. So about this project's really about the way symmetry appears in Floer homology. So I just want to say, before I forget anything else, parts of this are joint work with Yanki Lekili, and parts of it are joint work in progress with Nick Sheridan also. So with me, Lekili, and Sheridan. Okay. Okay. So, all right, so maybe I'll just try to bring people into this by just saying what kind of the ultimate goal is. Like, what's the kind of dream? Okay. And I'll try, and I won't be able to really get close to stating a theorem that is even remotely realizing this dream. But the dream is that you could use, let me see, I wrote a formulation down. So we want to use Floer theory, Floer homology, in the context of mirror symmetry to construct representations of, let's just say, a Lie algebra or a Lie group. Since it's a dream, I can just dream about doing it for groups. Okay, construct representations of a Lie group together with, and at the same time construct distinguished bases for those representations with distinguished bases. Okay. So, you know, this is of course a very important subject of representation theory, understanding representations of a Lie group or a Lie algebra. And one of the things that people in representation theory have been very interested in is, can you find interesting bases for representations? So, you know, there's many theories about how to construct representations, and there's also a lot of work by, you know, of course, most famous is by Lustig, also Kashiwara, Mirkovich-Volonin. I mean, and I don't even know all the different bases that are out there in representation theory, but there's a lot of interesting bases. And the ultimate goal of this project would be that we could use Floer homology to understand some of these structures. What's the Lie group going to be acting on? Well, in this statement, it's just acting on a vector space. Okay, well, I mean, but the dream is like presumably. Yeah. Okay. Clearly, I need to explain that. Okay. So I'll explain how this is going to go. All right. Okay. So you're wondering, you know, Floer homology of what? That's probably your question. Floer homology of what? Where will you see this? Okay. All right. Well, basic idea is this: that, you know, usually, you know, what you can have is you can have some group G. Okay, I'll just start to get into this, how this dream is going to work. So you have a group G, and let's say it acts on a space X. So G is some kind of algebraic group, let's say, and X is some algebraic variety. Okay. So what you want to do, whenever you have this situation, is you want to study the equivariant geometry of X. So you want to study equivariant geometry. One of the most important things to study is equivariant vector bundles. Okay. And, you know, I'll just say in words, you know, in representation theory, one of the ways to construct the representations of a semi-simple algebraic group is to consider its flag variety, consider line bundles on the flag variety, and take their spaces of sections. That's known as the Borel-Veil or Borel-Veil-Bott theory. So it's known that there are situations where if you pick the right G and X, you can get representations of G by studying equivariant vector bundles on X. Okay, so this is something that's interesting to study. Okay. Well, what's going to be so what we're going to do is, so this is going to be sort of the algebraic side for today, and it has a mirror partner. Okay, there should be some mirror symmetry. Okay. And what will be the mirror of x? Well, so the mirror of x was an algebraic variety. I'm going to have y, which is going to be some symplectic manifold. Okay. And depending on what type of algebraic variety you have here, it may not just be a symplectic manifold, it may be a symplectic manifold together with a function that we usually call the superpotential. Okay. The superpotential actually won't play that much of a role in what I'm going to say today, but so you can really think it's just a symplectic manifold. So we want to start translating things onto the other side, okay? So what do we want to say? So, for example, you have to explain what is, I mean, in fact, what most of this talk is going to be about is about, you know, what happens to this group action, right? What does that translate into? Okay, so you need a notion of equivariance. So the question, so one question is, you know, what is the notion of equivariance? Okay. Of the group action or the notion of equivariance. Okay, in the symplectic geometry of y. See, the thing is, if you, I didn't really say what x and y are, but in any case you try to figure out what they ought to be, you'll find that if G acts on x, G doesn't act on y. There's not really any group that acts on y. Okay, so it's a different notion. It's not just like, you know, you have some kind of group action on y and you're doing equivariant symplectic geometry. There's actually something fundamentally different happening. Okay. Let's see. Okay. So I want to see, you know, how can we see, the question is, how can we see equivariance in symplectic geometry? And I mean the thing that corresponds to this notion of equivariance. All right, so there's a couple things to say. So one thing I want to kind of recall, you know, maybe what are these equivariant vector bundles, just so people have a little bit of an idea. So what is an equivariant vector bundle? So if I have a vector bundle over x, let's see. Well, one way to think about it is this. I have a group acting on the base. I have this vector bundle. One way to think about it is that what you need to do is you need to lift the group action to the total space of the vector bundle, right? Because somehow that's something that may not be possible, and if it is possible, there may be multiple ways to do it. Another way to think about it is, maybe this is kind of, this works not just for vector bundles, but for also other types of sheaves. You naturally have, you know, you have the space X and you have a map. Well, actually you have two maps from G cross X to X. One is the action, you know, G acts on X, and the other is just the projection. And in order to make a vector bundle equivariant, you need to give an isomorphism between the pullback of the vector bundle under these two maps. Okay. So two things can happen. There's two questions. First of all, does there exist such an isomorphism? Okay. It may be that there is no such isomorphism. Okay. In that case, the vector bundle is not invariant and it can't be made equivariant. And the other thing is that if there is an isomorphism, you have to actually pick that. That's actually part of the data of an equivariant object. Now, we do know, you know, homological mirror symmetry does tell us maybe not what equivariant vector bundles are, but it tells us what vector bundles will correspond to. They're going to correspond to really Lagrangian submanifolds or more precisely, you know, objects of the Fukaya category. Okay. So you want to see how do you make an object of the Fukaya category, a Lagrangian submanifold of Y, equivariant? Okay, so what's the analog of this type of diagram here? Okay, so I'm not actually going to be able to do that directly. I have to switch the context a little bit because here we're talking about a group action. What I actually am going to be able to talk about is the infinitesimal version, so a Lie algebra action. So I have a group acting on X, right? I can differentiate it. I have the infinitesimal action. And I think of the infinitesimal action as actually just a map from the Lie algebra of the group to the vector fields on X, right, by differentiating the group action. Okay. So to begin this translation, I'm going to want to understand what are these vector fields. What is the analog of vector fields? Okay. Well, the thing is this. So here you have to get a little bit philosophical because, I mean, you can't just say, it's maybe not, you know, it's probably not clear what these things will correspond to, but you have to look at what you know, symplectic geometry can give you, okay? So symplectic geometry basically gives you this A infinity category called the Fukaya category. And you have to have some kind of notion of vector field that makes sense when all you have is a category. Right? You don't actually have a space. See, the thing is this, you know, the group doesn't act on Y. That's not the space where it acts. There's some kind of other gadget that it's going to act on. And the thing that it's going to act on is the Fukaya category itself. Okay. Okay, so what does this correspond, this vector fields correspond to? Well, if I have just, so the Fukaya category is just some A infinity category. Okay. And associated to an A infinity category, you have something called its Hochschild cohomology, or its Hochschild cochain complex. So let me just say what at least the chain groups are of that. How is my notation here? Right, so it's a chain complex. I'll just tell you what the chain groups are. It has a grading D. Well, here, maybe I'll do it first for an A infinity algebra. Okay, so I can kind of say what it is. So this thing is going to be, the degree D cochains are going to be the product over R greater than or equal to 0 of homomorphisms from A shifted by 1 tensor R to A, okay, of overall degree D. So where the map, these are homomorphisms, just linear maps from this space to this space of degree D. Okay, and that's the degree D Hochschild cochains. This, so your A infinity algebra has these operations. Mu1 is the, what I sometimes write D is the differential. Mu2 is a composition, mu3 and higher. Okay. And basically the differential on this space involves taking a multilinear function. You know, this is like a multilinear map from some tensor power of A to A. And you can basically take such a multilinear map and contract some of the inputs, combine some of the inputs using these mu operations. And that defines the differential. Okay, I'm not going to write out the complete formula because it's rather lengthy. Okay. Okay, so when you have an A infinity algebra, you naturally have this other complex associated to it. And there's a definition, which is that what's called, so there's something called an NC vector field, sort of on A, if you will, on this A infinity algebra, is a degree 1 cocycle in this complex. Okay. So if you have an A infinity algebra, I'm kind of just throwing this out there, you know, that's what we're going to call a vector field. All right, why is that a reasonable definition, right? That's the question. Well, okay, the reason why it's a reasonable definition is, I would just start with the following observation, which is that what if I took A, I'll write straight A instead of curly A, what if this was just a commutative algebra? Okay, so it has no grading, it's just like a ring that you learn about in ring theory. Okay, so what is its Hochschild cohomology? Well, it's actually an easy calculation from the definition, if you just figure out what the definition is, that this degree 1 Hochschild cohomology of A is just the derivations of A. Okay, so that means maps, maps A to A, okay, it's a map X, I don't know how do I call it, phi from A to A, such that phi of AB is phi of A B plus A phi of B, right? Okay. So that's the degree 1 Hochschild cohomology of a commutative algebra. So, but derivations of A, what's the relationship to vector fields? Well, I think of A is equal to the functions on the scheme spec A. Okay. So what I have is I have this space, it's a scheme spec A, and A is the functions on that, and this derivation is really a first order differential operator on the ring of functions of this space. So, but a first order differential operator is a vector field. So this is vector fields on spec A. Okay. And this notion of NC vector field, maybe I'll just say this is the motivation, is just sort of a broad generalization of that. You have a question? Yeah.
Shouldn't there be some kind of like constraint where this thing should live in the Hodge filtration? Because if your scheme's not affine, then you'll get H1 of OX.
I suppose you have you have a point there of whether it's really, so if it's not affine, would such a thing really be a vector field? No. It's true that if you just consider, so if you consider an affine scheme, these things are vector fields. If you consider a non-affine scheme, these things are not necessarily vector fields. They also have like H1 of O in there. But for simplicity, I'm just gonna take the simplest definition possible. I'm just gonna include, because in the case of chi category, I don't really have a way to tell where it lives in the Hodge filtration, as far as I'm gonna talk about today. So I'm just gonna throw them all together and say they're all some kind of vector field. Yeah. Okay. All right, now if you do this for a category, you can say, so let's just take one of these B's and let's try to see what you get out of it, because it's kind of implicit here. So let's say B is one of our NC vector fields. NC vector field. Now, what do you get out of it? So I did this for an A infinity algebra here, because I wanted to write this. If I'm doing it for an A infinity category, I should really replace this symbol A by something like, well, if I'm being just kind of, I'm just saying replace it by the direct sum of all the Hom spaces in the category. So when you think about, when you pass from A infinity algebras to A infinity categories, you should think that it's the Hom spaces in the category that play the role of the algebra. Okay, so if I consider L, let's say A is this is an A infinity category. If I have L in ob A, my B, part of the data is that B should determine an element B. So I take the sort of so this superscript here is the R in this formula. It's the arity, the number of inputs. Okay, so I get something that has no inputs and one output, and that output will live in the degree 1 morphism space from L to L. So this is all called B0 restricted to L. Okay, if I have an object, you get an element of the endomorphisms of that object. And if you have two objects, L and L prime, okay, in ob A, I get a map B1. This means it has a single input, so I'll say, well, you'll omit the L and L prime from the notation, okay, but this is actually a linear map from, it's a linear endomorphism of this Hom space, okay? And then you have B2, so if you have 3 objects, you have B2, et cetera. Okay, so it has sort of higher order terms. But these are going to be the most important for this notion of equivariance. Okay. So using this, you can give a definition of what an invariant object is and what an equivariant object is. Like, whether you should think that this NC vector field, you should think, okay, it's like a vector field. So, you know, it really defines a flow, okay? And the question is, if I take an object and I flow it by the vector field, does the object deform? Does its isomorphism class change? And really, that deformation class is measured precisely by the cohomology class of B0. Okay. So here's the definition. So this definition is originally, well, I'm going to reference Seidel and Solomon, okay, who really started setting up this, you know, explain, you know, really all these ideas are essentially contained in their work. So, Seidel and so their definition is that L, this object, is invariant if the class of B0 restricted to L, you know, for B, I should say with respect to B, if this class in H, okay, it'll live in degree 1 of Hom A, you know, if this is 0. Okay. So if that cohomology class vanishes, then it's what's called invariant. That means that the flow of this vector field, so to speak, doesn't change the isomorphism class of the object. And then to make it equivariant, you need to choose a cochain that kills this class. Like, you need to explicitly write it as a coboundary. So L is in. So yeah. Oh, you can't see this. Sorry. Maybe I'll. Sorry. Yeah. I would have to like move the whole board. Okay. And so an equivariant structure on L is a choice CL in degree 0 endomorphisms of L such that the differential of CL equals this chain you wanted to kill. Okay, so if you explicitly kill it, then you get a pair. So the equivariant object should be a pair consisting of an object and a cochain that kills the deformation class. Okay. Here, maybe I'll move over to this one. Maybe I'll push it up so that we can see it. So this is kind of an answer to, again, this was a framework for trying to understand the question of what is the notion of equivariance in the Fukaya category that corresponds to the notion of, you know, like equivariant vector bundles on an algebraic variety. Okay. So now, all right, what I've really talked about so far is really just abstract algebra. You know, what I like to say now is, you know, where do these NC vector fields actually come from in symplectic geometry? Like, I have to have a way to produce them if I'm ever going to use them in symplectic geometry. Well, so there is a very natural source for NC vector fields. So in symplectic geometry, NC vector fields come from symplectic cohomology. Okay. That's via, and I could say more. I could say via the open-closed string map, or via the closed open string map. Okay. Okay. So, all right, this might be a little bit closer to what people in the symplectic geometry seminar are familiar with. Certainly, I'm more familiar with this stuff. So, what you have here, so symplectic cohomology, this thing here, it's a theory that goes back to work of Chili, Bach-Fleur, and Hofer in the 90s. Well, the way this is, the version that I'm going to be using today is really for, these manifolds, non-compact symplectic manifolds. So in fact, the Y's that we're going to consider are non-compact symplectic manifolds. And Y's that have an end that's modeled on the symplectization of a contact manifold. So here's Y, here's some sigma contact type hypersurface, and I want the end here to be modeled on sigma cross 0 infinity. So the symplectization of a contact type hypersurface. So if this is the coordinate r, I'm going to choose Hamiltonians that are, generally speaking, on the end they have the form, well, I could just maybe I'll just go ahead and just do 1/2 r squared times a constant. Okay. So I have a symplectic manifold. It has sort of normal form on the end. I have a distinguished Hamiltonian function, and then my symplectic cohomology, or maybe I may have to use the chain level, is going to be the Hamiltonian Floer homology of that function. Okay. Okay. So now, if you want to know what this is, okay, basically the generators, the main thing that you pick up here is you pick up, so I'll just say this to get a rough idea of what's in this thing. It picks up the cohomology of Y, and also it picks up Rabe orbits in sigma. Right. So anytime you have closed, so roughly speaking, closed Rabe orbits in sigma are going to give rise to generators of this chain complex. Okay. So geometrically, these closed Rabe orbits I think of as kind of the most interesting ones. So geometrically, the source for everything is when your contact type hypersurface has closed Rabe orbits, and those give rise to, well, co-chains in symplectic cohomology, and if they are closed, they give rise to NC vector fields on the Rapp-Fukaya category. Well, okay, degree 1. So if, maybe I'll write this, if beta in SC1 of Y is closed, I mean this thing is a chain complex, right, with the usual Floer differential, is closed, then beta gives rise to an NC vector field on the Rapp-Fukaya category. On the Rapp-Fukaya category. Okay. Okay, the Rapp-Fukaya category is, it's actually defined very similarly to symplectic cohomology. I mean, the key thing is this function here that determines how the Lagrangians are perturbed at infinity. So basically, if I was doing the Rapp-Fukaya category, I would consider Lagrangian submanifolds that kind of come into the interior here. I might have 2 of them. Okay. And when I want to compute their Floer homology, I don't just consider the intersection points of these Lagrangians, but I also consider these Rabe chords They go from one Lagrangian to the other, or they might kind of go and kind of spiral around the manifold a lot and then end up on the other. So Rapp-Fukaya category is kind of, I think this symplectic cohomology and the Rapp-Fukaya category use the same geometry at infinity, namely the flow of this Hamiltonian, this quadratic Hamiltonian, to define what the generators are. Okay. Now how does this work? So I need to say, where am I going to get this B, right? How am I going to get that B out of a class in symplectic cohomology? Well, what you're going to use is you're going to use this closed open string map. What that means is that, here, I'll just draw a picture here. So consider the following Riemann surface, okay? Okay, so what we have up here is we have several boundary punctures. So this is really a disk with r plus 1 boundary punctures, and it has one interior puncture. Okay, so I'm going to put some elements x1, x2, x3, dot, 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 xr on the, so I think of these punctures here on the disk. There are r boundary punctures that are kind of drawn at the top. Those are, maybe I should draw the boundary in red so it's kind of it doesn't all look like boundaries. So this is the boundary of the disk. Okay. So I have these punctures up at the top. Those are my inputs from the Rapp-Fukaya category. That means each of these symbols represents a chord going between two Lagrangians. There's really some Lagrangians here. I could put those labels in as well. So here's, L0, L1, L2, dot, dot, dot. Okay. LR would be the last one. So I consider, okay, I'm decorating the domain still. I decorate this interior mark point with beta, and then the output is down here. I'll call it y. Okay, so my intention of putting this picture up on the board is I'm trying to define a linear map that has inputs, r inputs from the Rapp-Fukaya category, one input from symplectic cohomology, and an output in the Rapp-Fukaya category. And I do that by drawing this Riemann surface and decorating with a bunch of different conditions. So the boundaries of the Riemann surface are supposed to map to the Lagrangians. These punctures are supposed to be asymptotic to these chords. And this interior puncture should be asymptotic to the Rabe orbit, or Hamiltonian orbit, actually, when you think of it as Hamiltonian philharmology, the Hamiltonian orbit that represents the class beta. And by counting that map, so if you count these, and that defines the BR, right? Yeah.
Like in tensor product of vector spaces, what the linear map this counts are giving there?
Yeah. I mean, basically it maps from, maybe I'll do it up here. We map from SC, I mean, you want to just know what are the inputs and the outputs and stuff.
Yeah.
So it's SC1 of 1, or SC, you could do it anywhere. Tensor the Rapp homology of L0, L1, tensor Rapp homology of LR minus 1 LR to Rapp homology L0, LR. And this is what this is. And so so that's the whole map. That's what, and then what I do is I fix this thing to be beta. So I kind of, fix beta, and then I get a map from sort of r factors here to 1 factor there, and that's that Hom degree d a bracket 1 to the r to a. Okay, so this is here is called the open closed. So this general process is called the open closed string map, or closed to open, because you start with a closed string, this beta, and then end up with something in the Rapp-Fukaya category. Okay. So that's the point. So these orbits, it's amazing. These orbits, if they have the correct degree, they give you these NC vector fields. Okay. Let's see. All right, so so maybe I should give you an example of how this goes. Okay, so, and it's going to kind of try to, so I had that dream about realizing representations of a group in terms of Floer homology. Well, I'm actually only going to do it for a Lie algebra, but I'm going to, to a certain extent, realize that dream in the case where the group is SL2. Okay, so, which is the simplest semi-simple Lie group. Okay, so let me say what happens here. So what is the space that SL2 naturally acts on? Well, there's the flag variety of SL2. Okay, so if I write group SL2, it naturally acts on SL2 modulo its Borel subgroup, which is just a projective line. Okay. Now, what's the mirror of that? The mirror of that, so this is the X. Okay, this thing is the X. Hope I haven't overloaded X, but okay, so the mirror is Y, which is C star, non-zero complex numbers, and it comes equipped with the superpotential, which is just Z plus 1 over Z. Or here, I'll call it X plus 1 over X. Okay. Now, the superpotential, like I said, I'm not really going to be able to say much about it today, but it's there. Okay. Let's see. So now I have associated to this, I have, things like the ramped Fukaya category of Y of C star. Okay. I have the symplectic cohomology of C star. Okay. And I'm supposed to somehow figure out some interesting elements in here, degree 1 elements, closed degree 1 elements, and I'm supposed to get some interesting vector fields on this on this ramped Fukaya category. Now, I'll just remind you, what are the vector fields on X? So what are the vector fields on P1? The vector fields on P1, so if you choose Z to be an affine coordinate on a chart in P1, you can write the vector fields on P1 in the following way. You can write as dz, z dz, and z squared dz. You find these are so where z is a affine coordinate on P1. And these things actually generate a Lie algebra, which is isomorphic to the Lie algebra SL2. Okay, so that's kind of a simple calculation in the geometry of P1. Okay. Okay, so now, what am I going to do? Oh, right. Yes. Okay. Maybe I'll just continue. I actually forgot to say something when I was talking about that Seidel and Solomon thing, but I'll do it after this. Okay. So what is the symplectic cohomology of C star? Well, actually, this can be computed by Viterbo's theorem. Okay, so Viterbo has a theorem for what happens when you take the symplectic cohomology of a cotangent bundle. So C star is the cotangent bundle of S1 symplectically. And so the theorem says that this thing here, this SH star of C star, is isomorphic to the cohomology of the, not the cohomology, the homology in dimension, I guess this 1 minus star with my conventions, of the free loop space of S1. Okay. So that tells you what it is as a vector space. That's not that difficult to compute. I'm actually going to tell you what it is as a algebra. So I'm going to write the following. So the way these formulas make sense, okay, I didn't say this yet, but symplectic cohomology is not just a vector space. It's actually a ring. So it has a commutative product given by the pair of pants diagram. And more than that, it's what's called a Batalin-Vilkovisky algebra. And that means that it also has a Lie algebra structure. Okay, that's a consequence. So I'll tell you what this thing is. So it actually is supported in 2 degrees, degree 0 and degree 1. In degree 0, you just get Laurent polynomials. Okay? And in degree 1, the degree 1 is actually, it's a graded ring. So degree 1 is a module over degree 0, and it's a rank 1 module. And I'll write it this way. Okay. And you can describe, so del z is just a symbol here. It corresponds to the del z in the vector fields on P1, which I'll explain. Okay. So if you want a picture of where these generators live, okay, here's C star drawn as a cylinder, drawn as the cotangent bundle of S1. If you take your Hamiltonian that wraps at infinity, what you'll find is that, okay, you get some kind of constant orbits. There's some place where H has critical points, so you get some constant orbits. Then I'll get some orbits that wrap around the cylinder 1 time, some orbits that wrap around the cylinder 2 times. On the other end, they wind in the opposite direction. Okay, so I'll sort of denote these by integers corresponding to the winding number of the orbit. And what you find is that each of these orbits actually gives rise to 2 generators in the symplectic cohomology. Okay, because here when you draw it this way, this is the flow of an autonomous Hamiltonian. To actually define symplectic cohomology, you need to introduce a time-dependent perturbation that breaks the reparameterization symmetry. So that actually breaks each of these circles into 2 orbits. And the generators you get, so corresponding to the constant orbits, you actually get 1, the identity element in the ring. And oddly enough, you get this guy, z del z. Over here you get z squared, and then it's like, so that'll be z squared del z, z cubed del z, z to the minus 1. This one's z del z. This is just del z, sorry. Z to the minus 2, z to the minus 1 del z. Okay. So that's what the calculation looks like. All right. So in fact, okay, let's see. So in fact, you do see the vector. So let me explain maybe the notation. Okay, because yeah. So the notation is these products. That's defined with respect to the product on symplectic cohomology. The reason why I write del z is, I guess I'm kind of prejudicing the thing I want to say, which is that the SH1 intrinsically has the structure of the Lie algebra. So SH1 has the structure intrinsically in symplectic geometry, has the structure of a Lie algebra. And the notation kind of tells you what the Lie algebra is, right? Because these things here are actually vector fields. Actually, what I've drawn here, this whole row here, these are vector fields not on P1, but vector fields on C star. They're vector fields on C star because, like for example, if this one has a pole at 0, turns out that vector field has a pole at infinity. Okay, so I've written it in such a way that I'm actually kind of telling you what the Lie bracket is. It's that these symplectic cohomology elements bracket the way the symbol would bracket if you just treated it as a vector field on C star. Okay. And in particular, you do see this SL2 sitting inside there as those 3 vector fields. Okay. I'll go over here. Okay. All right. Now, I want to talk. So these are. So these classes here, they give rise to these, they are closed classes in degree 1 symplectic cohomology, so they give rise to NC vector fields on the Rapp-Fukaya category of the cylinder here. And we could ask, what are some equivariant objects for that Lie algebra, for those elements? Okay, well, really, I've only talked so far about one particular element, so I can talk about what are some equivariant objects. All right, so if I have, now I want to talk about equivariant objects. Okay, so let's see. So the thing, so let's see. Yeah. Yeah.
I'm kind of a little confused.
Yeah.
So you kind of started to ignore the superpotential, which makes this thing just kind of not, this doesn't have an SL2 action anymore. It's not
You're right. You're right. It doesn't have a SL2 group action. It has an infinitesimal SL2 Lie algebra action.
Oh, it still does?
Yeah.
Oh, I guess that makes sense.
So yeah, this is not just a technical point. It's actually kind of a fundamental question. Is how do you really see? Yeah, the story I'm telling right now, just ignoring the superpotential. That means I'm kind of sort of throwing away a divisor on this side, and you have to figure out how to put the divisor back in. Yeah, that's right. And that means you're not exactly going to be considering this symplectic cohomology. You have to change. Yeah, so I'll make some comments about that. Okay, so equivariant objects. So here's a proposition. Okay, let's say it. Let me say this. So the objects that we want to consider are the following Lagrangians. So this one I'll call L of 0. It's kind of just a straight line in the cylinder. And then I'll also consider some other Lagrangians, like this one here. Okay, call that one L of 2. Okay, and you also more generally have L of n, which is the thing that winds n times around the cylinder. Okay, so you get many different Lagrangians like this. And so here's a proposition. So this is from my paper with Yanki and Lekili. So these objects can be made as objects of the Rapp-Fukaya category, can be made equivariant for every beta in SC1 of C star by choosing CL equals 0. So choosing those, so remember, to make an object equivariant, what I'm saying is I pick any element of this SC1, any one of these things. I map it into the Hochschild cochain complex via the open-closed string map, that map there. I get an NC vector field. And then I have to look at this class, B0L, restricted to L. No, B0 restricted to L. And what I'm saying is actually that class just vanished. If you set it up properly, I mean, you have to choose your perturbations properly to make this statement true. But if you set it up properly, you can actually choose, you'll actually find that B0L is exactly equal to 0 as a cochain, and then you can choose CL equals 0 as well. Okay. Okay. Now's the point where I have to come back to something that I kind of just skipped over, which is that, well, why do I care about making an object equivariant? Because if I take two equivariant objects and I take their Hom space, like I take homomorphisms between equivariant objects, that vector space will carry a group action. That's actually the purpose of, that's how we get representations from equivariant geometry. Okay. So that really should have come, after this definition. So how do we get a representation? So if L CL and L prime CL prime are equivariant for B in CC1 of AA, as it were, then you get an endomorphism of the Hom space. So I get a map phi, which is an endomorphism of Hom A, like at cohomology level, Hom A L prime. And how is it defined? So it's defined by saying phi of x. What you do is you take your NC vector field B. So remember, B0 is just an element of this Hom space. Well, there's also B1, and B1 is an endomorphism of this Hom space. Okay? B1 of x. But actually here's the thing. You might think that this is all there is, because I said B1 is an endomorphism of this Hom space. Well, actually, it's not an endomorphism of this, because this is cohomology. It's an endomorphism of the chain level Hom space. But it's not necessarily a chain map. So that means it doesn't give you an endomorphism of the cohomology level Hom space. So instead, what you do is you use these cochains CL to correct it to a chain map. Okay. So, and I just multiply by CL prime on the left, and then multiply by CL on the right. And that expression, if you use the fact that B was a closed element of Hochschild cohomology, that is a chain map. So that actually does define this endomorphism. Okay. Now, there's also another wrinkle. So this definition is in the Seidel-Solomon paper as well. There's another wrinkle when you consider sort of multiple vector fields at the same time. So what I actually mean here is not just that you pick one element and it becomes equivariant for that element, but actually it's simultaneously equivariant for the entire algebra SC1. And that requires some kind of compatibility condition. Basically, one way to think about it is, you have this algebra, it's generated by these different elements. So you can, if you think about the vector bundles, this algebra is generated by these different elements. So you can lift each of them to an action on the vector bundle. But of course, the group, is not free, so there's a compatibility condition between the actions of the different elements. And you have to have a condition there. So in general, so I'll say, so actually when you have more than just one element acting on your, when you want to consider equivariance for a larger algebra of vector fields, you need consistency conditions. Okay, so maybe I won't write down the consistency condition, but you need that, and you also have to check it, and that's also part of the content of this proposition, that you can check those consistency conditions, and it's really equivariant for the entire algebra. Okay. So this proposition is telling us that this space, this Ramphler homology of, I could take two of these Lagrangians. Let's say I'll take L0 and Ln. This thing is a representation of, in fact, this Lie algebra here, vect C star, or SH1 of C. So here's a theorem, also from this same paper here. So the representation, this representation of SH1 of C star So you make them equivariant using these choices. Okay, so that gives you a representation. So the representation of SH1 of C star on this vector space is isomorphic to the representation of this thing, vector fields on C star, where this C star is really an open set inside that P1, acting on a certain space of what are called densities. So it's acting on a space Vn, which is the set of all densities of weight negative n over 2. So I'll explain this. So, okay. Okay. So, okay, a density of weight 1 is basically like a symbol, you know, function times dz. A density of weight, well, you can also consider densities of other weights, like for example, here if n is this number, and here I get minus n over 2, okay? And you can define this basically, you know, because you have vector fields acting, you can just do a sort of formal calculation of what happens when you differentiate this symbol by a vector field, okay? And so the space I'm considering is actually Laurent polynomials times the symbol dz to the minus n over 2, okay. So that's actually a pretty interesting representation, because if you take that representation and you restrict it to the SL2, remember there's an SL2 sitting inside this thing. So if I take the restriction to SL2 of this V sub n, I get some infinite dimensional representation of SL2, but actually it contains the irreducible representation as a submodule. It contains the irreducible representation of SL2 of highest weight. N. Okay, that's actually just an algebraic fact. So you can actually identify, if you just think about, you know, what happens when you take these expressions and restrict the action to SL2, you'll find that there's actually a submodule of dimension n plus 1 that's isomorphic to the irreducible representation of SL2 of highest weight n. All right. And now you can ask, what does this thing? Now here's the interesting thing. Okay. So we did this thing was just algebra, but then you can ask, okay, but we actually can explicitly compute the action in symplectic geometry. So what does this correspond to? All right. So in symplectic geometry, what this corresponds to is actually, I had these two Lagrangians. Okay. Here's another one. Wraps around, say, n times. Okay. And you get certain generators in the Rapp-Floer homology corresponding to the intersection points between these Lagrangians. And you also get other generators corresponding to chords. So that this picture actually kind of continues out here. Okay. You also get other generators corresponding to chords. And actually what you'll find is that this submodule here, this interesting SL2 submodule, corresponds exactly just to the things, to the set of generators that are actually honest intersection points, not chords. So actually you can geometrically identify this submodule in the Rapp-Floer homology. And the interesting thing is that it actually comes with a basis, right? Because when you think about it as intersection points of Lagrangians, you know, you think about your representation as spanned by the intersection points of Lagrangians. Well, then it actually has a basis, which are those intersection points. Okay. So I'm running a little bit short on time. I want to tell you, okay, so this was kind of, you know, this is a case where we can work this sort of picture out that you get from symplectic geometry, you get this representation. It comes with a basis, and it also has an intrinsic reason in symplectic geometry why it is a representation of this Lie algebra, okay? Because these are equivariant objects for this symplectic cohomology. So there's a couple new things that you need to do. So you raised a very important point that there's something kind of ad hoc about this, because first of all, I got this infinite dimensional Lie algebra, and then I identified this interesting finite dimensional subalgebra. You see that here too. I got this infinite dimensional representation, and I had to identify this finite dimensional representation sitting inside there. And that passage, where I say, oh, it has this interesting finite dimensional submodule, seemed a little bit ad hoc. Really, that's because I basically just forgot about the superpotential. If you understand properly, and people are trying to understand how to get that superpotential involved, I wanted to say, to get the superpotential involved here is, there's various, what you really need to talk about is what is the closed string sector of a Landau-Ginzburg model. And so, there's various proposals for that. One that's appeared at least in preprint form is due to Paul Seidel. There's another which is work in progress of Shil Ganatra and Mohammed Abu Zaid. And that when you have that, you can make more canonical. Where are you supposed to look for this finite dimensional Lie subalgebra? Okay, and the other direction to go is to do it for more general groups, right? So there is a prescription for what is the mirror of the flag variety of an arbitrary semi-simple algebraic group, and the work in progress is to understand how does this same picture work out. How do you see this Lie algebra? How do you construct these equivariant Lagrangian submanifolds? And how do you understand how do you get these representations from that picture? All right, I'll stop there.